Good morning, everybody. Today in class, we are going to start our discussions on Chapter 9, which is titled Solutions. Let's first define what a solution is. A solution is another word that we can utilize to define homogeneous mixtures. And we learned previously that when it comes to a homogeneous mixtures, we can have two or more substances that come together and they have a uniform consistency in which we cannot tell the different parts of our mixture. So that's why we call it a solution. Now, when we are making a solution, there's going to be two or more components of the solution. But understand that these two or more components, sometimes they can have more substances between them. Let me clarify what that means. So the major two parts is going to be a solvent. And when it comes to a solvent, understand that it's going to be the substance that is presented in greater amount. And when it comes to solvent, we have only one. In addition, when it comes to a solution, we can have a solute. You need at least one solute. So when it comes to the solute, you can have one or more. And solute is going to be the substance that is present in lesser amount, okay? So whenever we have a solution, you can have one solvent, one solute, or you can have one solvent and multiple solutes, okay? The reason why a solution can be created is because we understand that the solute is going to have attractive forces by itself. The solvent is going to have attractive forces by itself. Now, when we are forming that solution, okay, we need to understand that that solute and that solvent interaction has to be large enough to overcome the attractive forces for the components individually. So we can see in the right side of the slide, here we have the formation of a solution between salt and water, okay? Table salt is sodium chloride. So you can see that there's an anion and a cation. Now, water, on the other hand, has the following structure. In the formation of a salt water solution, understand that individually these items are going to have separate attractive forces. So let's just review attractive forces. Let me just post the following questions. What are the attractive forces in salt and water individually? So what would be the main attractive force found in NaCl? Let's put it in the chat. Remember that when it comes to the attractive force, is going to be either ionic, H bond, dipole-dipole, or dispersion. Excellent. So this is going to have an ionic attractive force because that's an ionic compound. When it comes to water by itself, okay, what's going to be the attractive force for water molecules? So if I have two water molecules, what's going to be the attractive force between them? The strongest. Excellent. Hydrogen bonding. Now, when we have salt and water combining, and we look at this at the molecular level, we know that sodium forms a cation, chlorine forms an anion. And I'm going to draw a couple of water molecules around them. Because water is a polar molecule, we can actually designate what portion of the molecule is going to be electronegative with a delta minus, or electropositive with a delta plus. So utilizing that designation, the delta minus is going to be the oxygen, the delta plus is going to be the hydrogen atoms in the water. So we know that salt and water can make a solution. If you put salt in water, like if you're trying to cook pasta, if you have an old school remedy for, like if you have a cut, I don't know whoever experienced this in a lifetime, but I for sure did. My grandma or my mom will put like salt water or straight up salt on a cut. Anyway, so let's say that you're making a salt water solution because you're about to cook something, rice, pasta, whatever you need to cook. Now, when we look at the molecular level of why is it that we can have salt water form, is because there's going to be an interaction between the cation and the anion with the partial charges of the water molecule. So the interaction that gives rise to the formation of the salt water is going to be that the delta negative of the oxygen will be interacting with the sodium portion, okay? Because since sodium is positive and opposites attract, then the area of the water molecule that is partially negative will be attracted to the sodium. In a similar type of interaction, the delta positive side of the water is what interacts with the anion, that chloride ion that we have here. So you can envision that hydrogen can interact with the chlorine or the chloride ion. Okay, so that's why we can have this solution, because you can see, and we're going to define what is this interaction, but at least to introduce the term, I'm going to write it here. This is an ion dipole interaction. Because you can see that the ion is going to come from the table salt, while the dipole is coming from those electronegativity differences that are between the oxygen and the hydrogen molecules that come in the water. So because of overall these interactions, that's why we can have salt water, okay? So even in these solutions, understand that there's a lot of chemistry that is present, okay? Now, understand that when it comes to solutions, solutions can come in all three states of matter, okay? So solutions can have solutes and solvents that may be solids, liquids, or gases. And in table 9.1, we have some examples of solutions. Table 9.1 is just trying to illustrate specific examples. So understand that that's not a table that I'm going to suggest that you guys need for the exam, but you should understand that conceptually, you can have solutions in all three states of matter. So the first example that we have is what we know as a gas solution. And since day one of the semester, we have learned that there are gas solutions present. When you have a gas solution, understand that your solute and your solvent are going to be in gas form, okay? So for example, air is an example of a gas solution, because when we look at air, and here I have a pie chart that illustrates what are the components of air, we can see that the majority, okay, of gas is actually nitrogen gas. There's 78% of it, okay? Then there's various solutes that are present in air, including oxygen, which is going to be the main solute, but there are other gases present in air. As you can see, we have argon, we have carbon dioxide, you even have water vapor. So understand that in the other gases category, there could be many, so we are just going to say that they're there. But understand that air is an example of a mixture, and nitrogen is going to be its main solvent. And then we have a variety of solutes present in it. Now, liquid solutions is the one that we are more familiar with. And whenever people think of liquid solutions, they think, oh, yeah, a solution, it has to be liquid. No, as you can see here, they can be in all three states of matter. Now, when we have liquid solutions, as you can see, you can have a gas in a liquid, you can have a liquid in a liquid, and you can even have a solid in the liquid. So the example that I gave in the previous slide represented a solid in a liquid, okay? Now, as you can see, a gas can actually be placed in a liquid. So for example, soda water, when you get carbonated water, that's when carbon dioxide is actually placed in water. Now, a liquid in a liquid, an example is vinegar, because vinegar has this compound that is called acetic acid, and when it's placed in water, okay, then that's what makes that solution. If you have any alcoholic beverage, vodka, tequila, all of those are going to be homogeneous mixtures. And similarly, you have an alcohol being placed in water, okay? Now, if we have solid in a liquid, as you can see here, we have sodium chloride in water, or we have iodine in ethanol. Let's understand that what makes a liquid solution is because your solvent is liquid. So again, the liquid solution comes from the idea that your solvent is liquid, okay? Now, you can see in the examples for liquid solutions that, you know, the majority of them, we have water as a solvent, but understand that not all compounds are soluble in water, and we are going to explore that later in this chapter. Lastly, we have solid solutions. When it comes to solid solutions, understand that your solute and your solvent is going to be solid, okay? So here we have the examples of brass, which is made out of zinc and copper, or steel, which is made out of carbon and iron. So if you remember, in terms of the classifications, these are going to be elements in the periodic table. So what is the classification of them? What is the classifications of zinc, copper, and iron? Because carbon is just going to be a different classification. What is the classification of zinc, copper, and iron? Is it a metal? Is it a non-metal? Is it a metalloid? Excellent, exactly. They are metals. And carbon, what kind of element is carbon? What kind of element is carbon? Excellent, exactly, it's a non-metal. The important thing here is not to generalize, because what I find time and time again is that some students decide to generalize. Oh, a metal and a metal, that's what makes a solid solution. Not necessarily, because you can see in the example of steel that you have a non-metal and a metal. The main thing here is looking at the state of matter between the solute and the solvent. If both of them are solid, that's what makes a solid solution. One more thing, homogeneous mixtures like brass or steel, they have a particular term that we utilize to define them. So these substances are called what term? What is the term that we utilize to define substances that are solid solutions, which is when we take elements in the periodic table, we physically mix them and they're not chemically combined? Excellent, yes, these are alloys. Bronze is another alloy, okay? And here you can see that instruments like the trumpet that you see here is actually made out of brass. So these are, materials that are utilized overall. Now, as you can see, specifically in the liquid solutions, water is an important solvent. And water is the most common solvent in nature. If it wasn't for the molecule of water, life on Earth wouldn't exist as it is right now. So understand that water is a very important molecule, and the concepts of things interacting with water is something that we are going to speak about throughout the semester, okay? Now, we know that water is a polar molecule, as I expressed a few moments ago, because the oxygen-hydrogen bond is a polar bond. When it comes to the water molecule, remember that the hydrogen, because it's less electronegative than the oxygen, then that's why it gets a delta plus. Okay, the oxygen, because it's more electronegative than the hydrogen, that's why it gets the delta minus. Okay, so that's why when we show them with the partial charge because of the dipole that exists in the bond. Okay, now the human body, as you can see, it is made on average about 72% of water. So that's why I was mentioning to you guys that the whole idea of interacting, molecules with water is so important because, for example, in the biomolecules that exist in our body are interacting with water as the main solvent that we have in our bodies. Now, when it comes to substances interacting with water, we need to actually establish how is it that we have the formation of these solutions. And the rule of thumb for making a solution in chemistry is going to be the idea that like dissolves like. What this means is that if you have something that is polar, it's going to dissolve that something is polar. If something is non-polar, then it's going to dissolve in something that it is non-polar, okay? Now, mentioning that, we need to also remind ourselves that because things that are polar have that dipole in it, that partial positive and that partial negative, that allows it to actually interact with things that are ionic. So again, rule of thumb, overall, polar molecules dissolve in polar solvents. Non-polar molecules dissolve in non-polar solvents. Okay, that's what we know overall. Now, When we go into the attractive forces, again, we are trying to make solutions that explain the behaviors of two things. We can actually look at interactions of things that are polar and how it behaves with other polar substances and even with ionic compounds. So I already mentioned to you guys how if we have an ionic compound that is soluble in water, for example, when we have table salt dissolving in water, there is an interaction between the cation and the anion in this system. Now, here we don't have illustrated the atoms, but I'm just going to write them in. In this diagram, what you observe is that the water molecule, it is illustrated in what we called in chemistry the ball and stick model, which you will use balls to actually define the atoms in the molecule. Now, the white balls are going to be hydrogen atoms. So let me write them in. And the red balls are going to be specifically the oxygen atoms. If I introduce to this drawing, okay, the idea of the partial charges that illustrate the dipole, then I can say, okay, that oxygen is delta negative compared to the oxygen atoms. So let me label them around the molecule. And as we learned a few moments ago, because the cation is a full positive charge and opposites attract, then the partial negative atom in my water is what is attracted to the cation. And the whole interaction is defined as ion-dipole interaction, okay? Now, polar molecules, the solvent and polar solvents, can also have the attractive force of H bonding. Again, I'm going to write in the atoms that we have here. So on the right side, we have a water molecule. On the left side, we have methanol. So the black ball is carbon. Carbon is bonded to 3 hydrogens. And then the oxygen is bonded to a hydrogen. Okay, so these are going to be the structures of them. I'm going to draw the Lewis dot structures for them. So you guys see the molecules that we're dealing with. So this will be your methanol. And this is your water, okay? Now, in this case, the reason why methanol and water can actually combine and make a solution, as you can see, is because of H bonding. If you look at methanol and you look at water, they have hydrogens that are bonded to quote unquote fun elements. Remember that fun is F-O-N. It's because that hydrogen must be bonded to fluorine, oxygen, or nitrogen. So now, because these molecules have those parameters, then we can say the H bond, that we can see it illustrated here, is because the hydrogen in the methanol can interact with the oxygen in the water, and vice versa. We can even say that the oxygen in the methanol interacts with the hydrogen in the water, okay? So those are two illustrations of hydrogen bonding events that can happen between methanol in water. Now, there is a specific parameter that has to be met in order for an alcohol to be soluble in water. It needs to have 4 or less carbons, okay? There's a question in the chat. Do they exchange hydrogen? Like if the methanol, so let me just clarify the question. Do you mean that the alcohol is going to pull a hydrogen from the water and act as a base? No, alcohols in water does not undergo such reactions, because what happens is that the willingness of a water molecule to release a hydrogen and the willingness of an alcohol to release a hydrogen is the same. So when molecules have the same willingness, that's is the concept of pKa, which is something that we don't deal in this class, but in upper level general chemistry courses, you do deal with those concepts. But going back to the questions, because these molecules have about the same willingness to donate a hydrogen, they do not donate the hydrogen to each other. They interact with one another via hydrogen bonds. And that's what we mainly see. Now, your alcohol needs to have 4 or less carbons in order to be soluble in water, because the minute that it has more than 5 carbons, then the solubility starts decreasing. But understand that this interaction happened between the 2 molecules. You can say that when you have an alcohol of 1 to 4 carbons, when it's interacting with water or being solubilized in water, making an aqueous solution, then there's going to be any of these 2 types of hydrogen bond present between the 2 molecules, okay? Now, there is a third type of interaction that can happen between water, okay, and a polar molecule. Or, sorry, that it can happen between polar molecules. Well, it can happen between water and polar molecules too, depending on the molecule that we're dealing with. Now, the last interaction that defines how is it that polar solvents are actually being able to be dissolved in polar solutes dissolving in polar solvents is a dipole-dipole interaction, okay? So we already established that methanol is going to be a polar molecule. Chloroform, which has the chemical formula CHCl3, and let me just draw the Lewis structure for it. Here, the carbon atom is in the middle of those green balls, and the green balls are the chlorine atoms. And then you see the hydrogen sticking out. So just imagine that the carbon atom is sitting in between all of those balls, okay? So chloroform is also a polar molecule, okay? So since methanol is polar and chloroform is polar, their interaction, which you can see it illustrated here, is going to be a dipole-dipole interaction. And this dipole-dipole interaction is going to be happening, okay, between the delta positive of the atom versus the delta negative of the other atom, okay? So when it comes to this, for example, we already determined, let me just draw the Lewis dot structure for methanol again. We already know that the polar covalent bond in methanol is going to be the oxygen-hydrogen bond. The oxygen is delta minus, the hydrogen is delta plus, okay? Now, when it comes to carbon and hydrogen, the carbon-hydrogen bond, it is actually nonpolar covalent. Let me go back into, electronegative, that's chapter 6. Carbon is 2.5, chlorine is 3.0. So here, the delta negative is going to be the chlorine, the delta positive is going to be the carbon, okay? So the actual dipole-dipole attraction between these two is going to be between the delta positive in the methanol with the delta negative of the chloroform, okay? And vice versa, right? You can say that the dipole-dipole interaction can be the oxygen atom with the carbon atoms. This is not only one interaction, it could be multiple. But the most important thing to note is that specifically because both molecules are polar, okay, the only way that we can have an interaction here is going to be a dipole-dipole interaction, okay, because of the delta positive and the delta negative of both molecules. Any questions when it comes to trying to determine how polar molecules are able to dissolve in polar solvents? Those are the three choices: ion, dipole. Let me just select a color to highlight this. H bond and dipole-dipole. Then let's move on to the next concept. Why is it that nonpolar molecules dissolve in nonpolar solvents? Okay. Now, you can see here that we have examples of nonpolar solvents. So hexane, toluene, or carbon tetrachloride are going to be examples of nonpolar solvents. And depending on what we're mixing, they could be examples of solvent and solutes because they're substances. Let me just call it nonpolar molecules. That would be more appropriate. Now, nonpolar molecules dissolve, as you can see here, in nonpolar solvents, okay? Now, individually, molecules that are nonpolar are going to have a specific attractive force, which is the strongest attractive force that they have. What is the name of the attractive force for nonpolar molecules? What is the strongest attractive force for nonpolar molecules? Let's put it in the chat. Excellent, dispersion. So when it comes to nonpolar molecules, the strongest attractive force is dispersion forces. So when you have a nonpolar, and in this case, this is just saying a nonpolar solid, and you have a nonpolar solvent, as you can see, the solid is going to be interacting with the solvent, okay? Now, The attractive forces that are going to define this interaction, like you guys just say, is dispersion forces. And when it comes to dispersion forces, remember that these molecules are going to have what we call temporary dipoles. And because these temporary dipoles appear and disappear, that's why we call them temporary. Having that ability of creating those temporary dipoles, since both molecules are able to have them, okay, that's what explains that they're able to form a solution. Just because both the solvent and the solute is able to specifically create those temporary dipoles, okay? Now, there's one last thing that we need to consider, okay? What if your molecule has polar and non-polar parts to it, okay? Then you can see that it depends on the molecule if we have what is called hydrophilic and hydrophobic competition to determine if they will dissolve or not. Now, let me show you a molecule that has polar and non-polar sides to it. This is oleic acid. Oleic acid is the main component that is found in olive oil, hence why we have the picture right there. Now, at the molecular level, when we look at olive oil and we look at oleic acid, we can define that oleic acid specifically has a polar portion, which I'm highlighting in gray. And it has a non-polar portion. Which I'm highlighting in red. So let's consider if we put this substance in water. A, two options. Does it form? Let me just put it as answers. That'll be easier. It will either form a solution or doesn't form a solution. So let's put in the chat, when you put oil and water together, do we form a solution or we don't form a solution? Great. I can see that a lot of them, a lot of you guys know that oil and water don't mix, Dr. Luz. We know that. But I just told you a few moments ago that if you're polar, then you're supposed to interact with polar solvents. But we know that water is a polar solvent, and wow, wait, oil actually has a polar portion to it. Why is it that oil and water do not mix? Because there is a competition between hydrophilic and hydrophobic. Hydrophilic means that you're in love with water. Hydrophobic means that you're afraid of water, okay? So when we look at oleic acid, we know that the non-polar portion is going to be hydrophobic. Because it is non-polar, okay? So it's going to be afraid of water because water is a polar molecule. The polar portion of oleic acid is going to be hydrophilic. It will be in love with water because they share that concept of being polar, okay? Now, this is the thing. The reason why we do not form a solution is because when we look at the molecule of oleic acid, we have to determine which part of the molecule we have in a greater degree. Meaning, what is more present? What is larger in terms of the number of atoms? The nonpolar portion or the polar portion? So which one is more present? Which one we have more atoms? Excellent job. The nonpolar portion. So even though our oleic acid may have the ability to interact with water through its polar side, well, not really, because the nonpolar portion of the molecule is so large that whenever we look at oleic acid at the molecular level, we say, you know what? Overall, this molecule behaves like a nonpolar molecule. And since the rule of thumb is polar likes polar, nonpolar likes nonpolar, then it makes sense that oil and water do not mix. So remember, when it comes to this, let me just write it in the notes. Since the nonpolar portion is larger compared to the polar one, the molecule behaves like a nonpolar molecule overall. Okay? Now, understand that this is not the case for all molecules, okay? Because as we're going to see in later chapters, there are ways in which we can actually take a molecule that behaves like this and all of a sudden it can solubilize in water. For example, detergents, okay? Which actually are made from oils, okay? We're going to learn that in chapter 15 when we talk about lipids, okay? Any questions on the rule of thumbs of how we make solutions by mixing polar molecules with polar solvents, or like you guys just saw illustrated, ionic compounds that are soluble in water by ion dipole attractions, or why is it that non-polar molecules need a non-polar solvent in order to make a solution?
Professor, I have one question.
Yeah, go ahead.
So like for the, like, let's say that like the oleic acid, if it had more like polar atoms, does that mean that it would be able to interact with water or still no?
It needs to have way more, because think about it. When it comes to oleic acid, this has 18 carbon. It has 18. Let me count them. Oh, wait, hold it. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, we have 18 carbons that we have to overcome. So if you want to make oleic acid be soluble in water as it is, there's two options. You introduce to the molecule, which you have to change chemically, okay? A lot of C double bond OH around the molecule, or the other option is that you make it an ionic compound. We're going to see in the lipid chapter how oils, once you make them ionic compounds via chemical terms, all of a sudden they can be soluble in water. As you guys know, like if you go and do your laundry, if you use those detergents, some of them derived from oil. So for molecules like this, you want them to solubilize in water, two options: make them ionic or create more polarity in them. But since making them ionic is a easier chemical strategy, usually that was the one that is preferred.
Okay.
But we're
Thank you.
going to learn more about that in chapter 15.
Okay, thank you.
No problem. Other questions about the rule of thumb of how we make solutions in these different interactions? So when it comes to ion dipole, there's a question in the chat about going over ion dipole. When it comes to ion dipole, this only applies to ionic compounds that are soluble in water. If you have an ionic compound that is not soluble in water, this is not going to apply, okay? So in an ion dipole situation, what we have is that my ionic compound has a full positive and a full negative charge, right? Because I'm in an ionic situation, I'm only dealing with cations and anions. So in the case that you have an ionic compound that is soluble in water, and if it's soluble in water, it's going to be soluble in other polar solvents, the interaction is that in the polar solvent, whatever atom is partially negative because of electronegativity will be attracted to the cation. The anion, which is not illustrated here, but I illustrated in the previous slides, the anion will be attracted to the electropositive portion of my polar molecule. So since we have full ions, meaning cations and anions, that's the ion portion of the term. And dipole is just, again, that separation that it is created by the difference in electronegativity in the polar bonds in a polar molecule. And remember, it's always, in terms of attraction, is the negative of one side, the positive of the other, is what makes that happen. Any other questions when it comes to how solutions are made? Excellent. So the next topic that we are going to talk about, as I kept on mentioning when we were looking at how are solutions made, is that not all ionic compounds, meaning salts, are actually soluble in water, okay? There are some compounds, okay, that actually form a precipitate, okay, when they are in the presence of water. So one of the type of reactions that we recently learned in the previous chapter was a double replacement reaction, okay? And when we have a double replacement reaction, like we see on the right side of the slide, we have potassium iodide reacting with lead-2 nitrate, forming potassium nitrate and lead-2 iodide, okay? We see that here in this image, we have the potassium iodide being added to a solution of lead-2 nitrate, okay? Potassium iodide is soluble in water. Lead nitrate is soluble in water, but when you combine them, they create this product, the lead-2 iodide. And as you can see, it has an S in the corner. So this forms a precipitate. Okay, that's the solid. In this case, it's going to be that yellow compound that you see that is formed here, okay? And the reason why that lead-2 iodide is precipitating is because it's not soluble in water, okay? Now, how do we know if a particular ionic compound is soluble in water or not? Well, for that, we need to know solubility rules. So in terms of solubility rules, you need to know this for exam 2. It's a must. We're going to have questions on solubility rules, okay? So let me just interpret you guys, or interpret for you guys what the information in this table, okay? Because sometimes students go through the table and they're like, but I don't understand how we determine what is soluble or insoluble in water, okay? So I'm going to make some notes to the table to clarify how do we use this table to understand if my ionic solid, or my salt in other terms, is soluble in water or not, okay? I'm going to divide these guys in groups, okay? So rule number 1 says that lithium, sodium, potassium, or ammonium, okay, as you can see, is always soluble in water, okay? Look that they have no restrictions, okay? So when those cations, lithium, sodium, potassium, or ammonium, are present in a chemical formula, it doesn't matter what is attached to. They are going to be soluble in water. If something is soluble in water, that's what we assign the symbol AQ. And remember that AQ means aqueous. So when it comes to this cation, any anion that is paired with them will be soluble in water, okay? Let's go to the next one. What about if I have the anion nitrate or acetate? So let me just write a note here. C2H3O2 minus, that is acetate. Okay. In the notes for the ones that I gave you guys, you may see it as CH3CO2 negative 1. It's the same thing. Okay, if you look at the atoms, it's the same number of atoms. It's just that in the first one, which is the one that is in the textbook, that's how you know, that's how you write it in inorganic chemistry. As an organic chemist, I usually write my acetate as CH3COO negative 1, okay? So on rule number 2, if in your chemical formula you have nitrate or acetate, observe that it says none. Okay, what the word none means is that any cation paired with them will be soluble in water. And again, the reason why I keep on talking about, either anion or cation is because we're talking about ionic compounds. So in the list that you see, there's a plus that is going to be paired with a negative, which is an anion. So in the second, it's, I have an anion. So then it has to be paired with a cation. Let's move on to the next one, which is chlorine, bromine, or iodine, okay? Chlorine, bromine, or iodine, okay, are always soluble, but if they're paired with silver, lead 2, or mercury 1, they become insoluble, okay? So to summarize this, any cation other than Ag+, Pb 2+, or Hg 2+ will be soluble in water. The 3 cations next to Cl-, Br-, I-, and what I mean with these 3 cations, it's going to be these 3. Will make a precipitate, okay? And if something is insoluble, we put an S next to it, okay? Any questions so far? Let's move on to the next set of rules. What about sulfate? Sulfate is soluble, but there are some pairs that make sulfate form a precipitate. And those are these 4 cations. So if you have barium sulfate, lead 2 sulfate, calcium sulfate, or strontium sulfate, those are insoluble, okay? So sulfate containing compounds are soluble in water unless the cation is barium cation, lead 2, calcium, or strontium. In chemistry, we refer to them as the heavy 2s, okay? Just because they live on group 2A. But note that not everybody in 2A is going to make sulfate insoluble, because, for example, magnesium, okay, which is right below beryllium, is the one out of all of the ones in group 2A that when you pair with sulfate, it is actually a soluble compound. So magnesium sulfate is soluble in water. For those of you that maybe for aches and pains use Epsom salts, magnesium sulfate is what makes Epsom salts. Because sometimes, like if you have aching muscles, that magnesium actually helps a lot. So understand that not everybody from group 2A will make sulfate be insoluble. It's only barium, calcium, and strontium, okay? Now, let's move on to the 5th group that we have here. That is what happens to carbonate, sulfide, phosphate, and hydroxide, okay? So as you can see, carbonate, sulfide, phosphate, and hydroxide are always insoluble, okay? Now, there is a way to make them soluble, and that is if as a cation, you pair them with the cations on group 1. Group 1 meaning what I label as 1 in this table: lithium, sodium, potassium, and ammonium. So these anions form a precipitate. When found in ionic compounds, unless they are paired with lithium, sodium, potassium, or ammonium. Then they become soluble in water. Okay? So you guys need to know all of these rules for exam 2. If you're given an ionic compound, you need to know if it's going to be soluble in water, okay, or not. So let's go back to the example that we have on the right side of the slide to actually illustrate, okay, why is it that we gave the assignment of aqueous or solid to the different components of this double replacement reaction, okay? We can see at first that we have potassium iodide, okay, as aqueous. Let's put in the chat what rule actually explains why potassium iodide, okay, is soluble in water. Let's put the number in the chat. What rule? Excellent. Number 1 can explain it. What other rule can explain it? Excellent. Number 3. Both of them can explain it. Number 1, because again, there's potassium in it. Boom. We have an aqueous solution. Number 3, because we have an iodide, and since iodide is not paired with that silver, lead-2, or mercury-1, then it's soluble. Excellent. Next one, lead-2 nitrate. Which rule, okay, 1 through 5, explains why lead-2 nitrate is aqueous? Excellent. Rule number 2. Rule number 2, because any compound with nitrate is going to be soluble in water, okay? Rule number 2 also applies to potassium nitrate. Actually, rule number 1 and rule number 3, rule number 1 and rule number 2 explain why potassium nitrate is aqueous. Let's put in the chat, what is the number that explains why is it that lead-2 iodide is a solid? Great job. Rule number 3, because as you can see, having an iodide ion makes you soluble, but wait, my iodide is actually paired with lead-2. That's why we have a solid, okay? So when it comes to this, understand that you guys need to remember the concepts of double replacement reactions. And for exam 2, if you're given different combinations, you need to be able to predict the product of your double replacement reaction and determine if the products will form a precipitate. A precipitate not always needs to be formed. And we're going to use solubility rules in order to do this. Let's do a couple of examples before we go on break. In the first double replacement reaction, we have silver nitrate and potassium phosphate. Let's put in the chat, what is the chemical formula for silver nitrate? Excellent. Thank you, Taylor. It's going to be HgNO3. Potassium phosphate. What is the chemical formula for potassium phosphate? Great job, you guys. K3PO4. In order to predict the products for this, we need to break each of these ionic compounds into ions. Hg is +1, NO3 is -1. Okay, so potassium is +1, phosphate is -3. Okay, put a 1 in the chat if so far it makes sense what we have done. I want to make sure that people follow this. Excellent. Since we have a double replacement reaction, that means that these compounds are going to exchange partners, okay? So my cation here will now be paired with the anion here. My cation here will be paired with the anion here, okay? So I'm going to write the new pairs. So we have Hg +1, and we have PO4 -3 plus K plus NO3 -1. So now that I've formed my new pairs, I'm going to write the correct chemical formulas for them, okay? So the chemical formula for this new pair is going to be Hg3PO4. The chemical formula of this new pair is just KNO3. Okay, put a 2 in the chat if it makes sense, the work that we have done. Excellent. So for these problems, okay, let me just write here. Sometimes it depends if I feel that we need to practice balancing equations, I make you guys balance these, or sometimes I don't. I just say, hey, write the correct chemical formulas for the product. And let me just establish something when it comes to that. If I tell you guys that I say that this is A and this is B, this is C, and this is D, and I want the products being written as A, D plus C and B, that's what I mean, okay? So make sure that you read the format. You don't want to miss points on doing the right work, but because you didn't follow the directions, then, because remember that Canvas, if I give you directions, is because Canvas is not allowing me to do so many of, you know, the combinations. So I need to, when I give you specific directions, you need to follow them. So when it comes to this, no problem. So if in the instructions for this question in the exam, it says in the double replacement reaction, when you predict the products, consider the first compound, the cation is A, the anion is B. In the second compound, the cation is C, the anion is D. Predict the products based on the first compound needs to be the chemical formula for the combination of A and D. The second compound needs to be the combination of C and D. I'm guiding you through the answer, but the thing is that you need to make sure that you write the correct chemical formula, okay? So your final answer is not the ions. The final answer will be these, okay? And again, I may tell you, go ahead and balance it, or I may say not. To balance this reaction, we just need to put a 3 here. We need to do a 3 here. And that's how we balance it. There's a 1 right here, and there's a 1 right here. But anyways, now the question is, we need to determine if here we have made a precipitator or not, okay? Remember, if something is soluble in water, we label it AQ. If something is not soluble in water, we label it S for solid. So if we go back to the rules that I just showed you guys, okay? Remember that the compounds in question here are KNO3 and then AG3PO4, okay? Let's get started with the first one, which was AG3PO4. So do we put an S for solid next to that silver phosphate, or do we put an AQ for aqueous next to that silver phosphate? What is that? Is that soluble in water or insoluble? Remember, if it's soluble, we put AQ. If it's insoluble, we put an S for solid. So we're doing this one, the silver phosphate. Is this soluble or insoluble? So S or AQ. Remember, S is for solid, not for soluble. So silver phosphate is going to be a solid in water. It's insoluble. Who tells us the rule that tells us that silver phosphate is solid, meaning forms a precipitate, is insoluble in water, is because of rule number 5. If you see rule number 5, having phosphate, so phosphate compounds are not soluble in water. The anion here is the phosphate. The cation here is silver. The only cations that make phosphate soluble is going to be lithium, sodium, potassium, and ammonium. So right now, okay, remember, solid means that it's insoluble in water. What about potassium nitrate? We already did it in the first example. Is that aqueous or solid? Excellent. We're going to put AQ. So when it comes to this, out of these two, this remains aqueous, which means that it's going to be in the water solution. But if we form the precipitate is going to be that silver phosphate. Okay. Let's do another example. Here we have calcium nitrate, and then we have hydrogen monochloride. We're going to learn in chapter 10 how even though hydrogen monochloride is a covalent compound, the minute that you put it in water, it actually can isolate into ions. So calcium nitrate, what is the chemical formula? Let's put it in the chat. Chemical formula for calcium nitrate. This is just practice for the exam. Thank you, L. You got the answer. CaNO3. That's calcium nitrate. What about hydrogen monochloride? Excellent, HCl. And again, let me just put the note here. This is just, I'm giving you a preview of chapter 10. Strong acids like HCl form ions in water. Okay, so we break this into ions, Ca2 plus, NO3, -1. This is going to be H plus and Cl minus. Again, cation of the first is now with anion of the second. Cation of the second forms a compound with anion of the first. So my two new compounds are going to be Ca2 plus, Cl -1. And on the other side, I'm going to have H plus, NO3, -1. Okay. So the chemical formula coming out of this is going to be CaCl2. The chemical formula coming out of this is going to be HNO3. Okay. Put a 1 in the chat if so far it makes sense to predict the products in this double replacement reaction. Excellent. So now let's take these chemical compounds, let's apply those solubility rules. Let me just erase it here. We're dealing with HNO3 and CaCl2. Okay. Is HNO3 solid or aqueous in water? Great job. This is aqueous because any compound with nitrate will be aqueous. What about calcium chloride? Calcium chloride. Calcium chloride. Great job. That is also aqueous. Because remember, the only thing that makes chloride, bromide, or iodide insoluble is silver 1, lead 2, mercury 1. Okay? So here, this is aqueous, and this is aqueous. Okay? So Roman numeral 3, we have a reaction that does not form precipitate. So if you were doing this in the laboratory, it may look like, oh, nothing happened. Well, the exchange of ion happens. It's just that the brand new compounds that are formed remain aqueous, okay? So you don't see the formation of a precipitate, but the indication that a reaction can happen could be the release of heat. So in a situation like that, you just touch the test tube, the beaker, wherever you're doing this reaction, and you'll be like, oh, wait, but it released heat. So a reaction did happen. It's just that visually no precipitate was formed. To balance this reaction, let me just put the coefficients. We need a 2 here and a 2 here. This is a 1 and this is a 1. Okay. Questions on Roman numeral 3? Put a 1 in the chat if you want to do Roman numeral 5. Okay, I'm going to give you guys 2 minutes to go through Roman numeral 5. Write the chemical formulas for the reactants, exchange the ions, write the correct chemical formulas for them, okay? You have to pay attention in the exam. If I say balance the equation, the instruction will say that. If I don't want you to balance the equation, the instructions will also say that, like, do not balance these equations. But for now, let's just write the chemical formulas of the two reactants. Let's write the correct chemical formulas for my products. Let's determine who is aqueous versus who is solid in this product. Okay, let's get started. Copper 2 bromide. Chemical formula is CuBr2. Aluminum chloride, AlCl3. When we break it into ions, Cu plus 2, Br negative 1, Al plus 3, Cl negative 1. We exchange the ions. Cation, anion, cation, anion. So we have Cu plus 2, Cl minus 1. So that will make CuCl2. And we have Al plus 3, Br negative 1. So that makes AlBr3. To balance this equation, we need a 2 here. We need a 3 here. And then don't have a medium. Two here. 3 here. Excellent. So let's get started with copper 2 chloride. Is that aqueous or solid? Just put it in the chat. Copper 2 chloride, aqueous or solid? Excellent job. This is aqueous. What about aluminum bromide? Great job. Also aqueous. So this reaction, oops. Sorry, skip. So this reaction also, there's no precipitate formed. So another indication of the reaction could be either absorption or release of heat, but we can only know that in the laboratory. Any questions on a reaction in which we are going to apply solubility rules to double replacement reactions? There's a question in the chat. How did you know what to put in front of the elements? Because I'm just balancing the reactions. So the coefficients in front of them is just to illustrate that we need to balance these reactions. As I mentioned when we started practicing these, if I feel that I haven't tested you guys on balancing reactions, I may, include it in these questions. I typically test you guys separate in balancing reactions. So when it comes to this, for me, it's more important that you guys know to correctly predict the product of the reaction and to know if it's aqueous or solid. So understand that the question may say you do not need to balance the reaction. In that matter, then remember that you need to just write the correct chemical formula and then put aqueous or solid in the answer. So just make sure that you read the instructions. Any other questions? Okay, so I'm going to stop our first half here.